Perfect. Okay, let's do it. Thanks, everyone. Yeah, so we'll be talking about what we are calling omnimodal action models. You can think of it as multimodal action models for physical and digital agents. So I'm Hirsch. If we haven't met before, this is Pranav, and we're working on this both as a startup called MedArc, but also with an open source research group named Manifold. So this is a collaboration with them and also with MIT and Georgia Tech and a couple other teams. We'll talk about that as we go further. So just a quick overview of this talk. It's kind of broken up into three parts. So first, I want to talk about what action models really are. This is definitely kind of like bleeding edge stuff. Even in the research, it's really new. A lot of work has been happening this year. Then we want to talk, I think Pranav gets to talk about the sort of brunt of exciting stuff, which is this new data set and benchmark and how we're thinking about the space and kind of our contributions. And then we'll give like a sneak peek around how we're thinking about how these action models map to really useful digital agents, which is something we're super excited about. So let's jump into it. So yeah, first I'm going to talk about agents and action models. So I think a lot of people scratch their heads on like what an AI agent really is. In the past 2 years, there's been a huge amount of interest. There's been a myriad of different sort of projects across from very specific areas like particular styles of software engineering or QA, all the way up to more generic sort of agents that should be able to do everything and are open-ended. Lots of teams have started working on this stuff. And if you talk to a bunch of researchers, they often say, oh, these aren't agents or these are agents. And they kind of like shake their fist at the rigor of what an agent is. They start to spout different sort of definitions, like a couple of them are here. So anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. You can say that's rigorous, but what the heck does that really mean? What's happening in that system? It's just saying it looks at things and it does things, and that's not that interesting. There's even more glib definitions, like an agent is really just a function that maps precepts, the big capital P, to actions, which again doesn't mean much. So these are like the definitions that are bandied about in like AI textbooks and things like that. Today we want to highlight a couple things. So one is really that there's like this spectrum of capability, even when it comes to thinking about these things foundationally. You have systems that are more reactive or reflective, which, starting on the diagram on the right, they kind of just operate in fixed ways with specific rules and conditions on environments. And then you kind of get more into modeling and trying to get this system to start to approach solving whatever problem it's in a more robust way. And there's lots and lots of different types of ways people have approached this. They think of these as, we might hear in the RL literature, policies. And this is really where LLMs have really been kind of shaking the agent world up in the past 2 years. All the way to, some, I guess, very high-minded AI researchers like to think that, oh, well, an agent should really be learning dynamically from its environment and doing a bunch of fancy sort of continuous optimization. And so a lot of people say a lot of different things, and we want to drill in on one particular theme here, which is action. So in all of these diagrams, I know they're a little small on the screen, you'll see that at the bottom, the agent is supposed to act on its environment. Well, what the heck is an action, and how are people building those kind of agents today? LLMs have been enormously impactful for unlocking the kind of agents I just talked about, right? Like, mainly because they operate in language, and language is a very powerful and general medium. So you suddenly have all these abilities where, even though it's not really dynamically updating itself from the environment, it still is able to adapt using things like in-context learning. Somehow it's able to reflect because it's able to represent things in language and then process that language again. It's able to plan. It's able to, I know a couple folks here are looking into memory, it's able to represent memory in language as well. But one of the challenges that a lot of agent companies, and of course researchers also still scratch their head on this, is how do you get agents to reliably do multiple tasks? Multi-hop actions is one framing for this. And so we're going to talk about the models that are being built specifically to solve this problem. And that's really where the terminology action model comes in. Before I jump into that, I just want to spend sort of like a 30 seconds on clarifying around function calling. So one of the interesting things that LLMs are able to do is they're able to function call. They're able to pass the right parameters to a given API signature, and then that API can be called and that tool can be used. And because this is all sort of a language representation, LLMs can do some of these in serial sort of steps. And so there's been a lot of work in enabling LLMs to get really accurate on this stuff. If you want to check out sort of state of the art on this, the project on the right, Gorilla, runs a function calling leaderboard that's really cool to see. And so you can see how well Claude does versus other things. I think it's just dominating. And companies like Cohere talk about function calling as tool use. And hopefully by the end of this talk, we can explain how we think about tool use and how it's something much more robust and complex than function calling the way it's formulated today. So what is an action? There's definitely this emerging notion. It kind of picked up after some kind of perspective pieces on technologies like ACT1, which Adept was supposedly developing a few years ago, or the LAM, large action model. Different groups have coined that term, Salesforce and Rabbit. People kind of posit this whole thing like we want to move from generation to action. But if you really think about it, what does that mean? How is it different to go, like what's a generation versus an action? And so one way to think about it, and kind of the way that we've been oriented on actions, is that an action in the context of an agent is a reliable completion of an objective. And that objective can be very atomic, can be composable, but it's the reliable completion of an objective without a human in the loop for that completion. Meaning this model or this system or this agent did something on its own. And the complexity of actions and the sort of multi-hop nature of them can basically compose from there. It's really natural to think about it in the context of embodied AI. And that's why a ton of the work that's been happening in action models is in the embodied AI domain, which we'll talk about in depth today. So I first want to kind of like motivate the sort of background context on the models that we're going to talk about today. So a couple of years ago, it's sort of a natural thing, right? As LLMs are starting to do better, you can imagine that back in 2022, there was a lot of smart researchers basically thinking like, well, what if we threw more data at the same architecture, and like, will it do well? How well it will do? Does the kind of data matter? Can we get it to do complex things like move a robot around or play a video game? And so that's exactly what DeepMind tried in 2022. And it was a paper called A Generalist Agent, long before people were hyped about agents, right? This is way before ChatGPT release. It's a great paper to read, but the idea was basically, can you take all these different modalities, vision, language, and in this case, they use terminology called control, which really represents reinforcement learning and robotics simulations and or real data. Can you figure out how to map it all to the same sort of GPT-2 style architecture? And then can it then spit out things that make sense in the same way that transformers are trained? So next token prediction. But do those tokens actually map out to anything reliable? And so that's really what the Gato contribution was. And the results of that were that Gato performs reasonably well. It wasn't breaking any benchmarks on many of these tasks, and we will go really deep into what these tasks are. It relates to the work that we've been doing. But it did reasonably well, and that was a big sort of insight because that meant that transfer learning in some of these architectures can work. Of course, it took the world a couple of years to kind of like orient around this and really push this forward. And this year, there's been a ton of breakthroughs in this emerging category of action models that they call VLAs, Vision Language Action Models. Move on forward. Real quickly, you may be wondering, like, how does a model like this handle an action, right? Like, how does it work? Well, really, for a lot of the architectures that we're going to talk about, they look at it the same way that an LLM looks at text tokens. So these are basically, they come up with some sort of language to represent the different actions that a model can take, whether that's like moving a robot arm 2 degrees to the left, or, you know, hitting the button in a video game or a specific jump or something like that. They map it to a shared language, and then it's processed in a really similar way to how LLMs process sequences. So these are sequence-to-sequence setups. Cool. So in the past 6 months, there have been some really profound sort of advancements in this area. People are starting to call these architectures vision language action models. And so we're just going to overview a couple of them, talk about the meaningful insights into them, and how they build up towards the exciting stuff we have to share today. So first, let's talk about RT2. So RT2 is kind of like Google's flagship model in this space until pretty recently. In a way, it's a successor to the Gato model that we just showed, except RT2 focuses mostly pretty much entirely on robotics tasks. So the real insight of these VLAs today is not necessarily focusing on a bunch of varied multimodal tasks, but rather, can you use internet scale text and vision data to somehow augment these models? Is there some knowledge that's preserved and shared internally in these models when you train on that, that can then actually be used to improve transfer in robotics tasks? And so these models are trained on tons of actual real-world robotics trajectories from a data set called OpenX, which we'll talk about in a lot of detail shortly. But that was kind of the big breakthrough, and RT2 does a good job on a lot of transfer tasks. One thing to note is how are actions represented? So we talked about the token sort of level representation of actions, but really in a lot of these architectures, including RT2, actions are mapped to language, basically. So I just wanted to highlight that what's going in and what's coming out of this model isn't unlike language. It may be language-specific tokens that represent specific actions, but it really still is doing a language prediction task. Cool. RT2 was a really big model. There are actually two variants. And so naturally people wanted to see, well, can you sort of build much smaller models and try a couple different techniques? So Octo was another paper that came out, I think earlier this year, like a few months ago, maybe in May or something. And it focused on actually pre-training and fine-tuning new kinds of models, including adding sort of other processing techniques like a diffusion layer into that model, but to basically efficiently do a bunch of robotics tasks. And it performed quite similarly to the 55 billion parameter RT2, except Octo's largest model was, I think, 53 million parameters, or maybe 93 million parameters. So orders of magnitude less in complexity of the actual model, but accomplishing similar results. And OpenVLA is currently SOTA in this area, I believe, though the area is moving fast. So OpenVLA was another VLA that has come out in the past 3 months, and it basically, the real insight with OpenVLA was you actually don't even have to do too much training and pre-training from scratch. You can take a ton of vision encoders, vision models, and a large language model backbone, in this case Llama 2, and with a fairly efficient fine-tuning, get it to perform better than RT2. They also did some clever things like swap out. I kind of like threw the baby out with the bathwater early, but they were kind of like one of the ones that shared this detail of swapping out a bunch of the less used language tokens in the encoder for this transformer with actions directly, and it worked, which was pretty cool. So you're able to actually collect, there's a fair amount of useful information in this multimodal space that can then be used in these robotics action-driven scenarios. And I keep emphasizing robotics here for a reason. Let me go one forward. And that is that all of these action models that we've described in the past 6 months, which are really being called action models openly by the research world as well, are oriented at robotics. So none of them are being evaled back on multimodal tasks or interleaved multimodal tasks. They're being evaled on these robotics tasks, which you're going to see in a lot of detail today. And that's really useful for people who are trying to build humanoid robots or robot arms that behave really reliably. But our perspective is that actions are so much more useful and can basically be transferred into many other kinds of scenarios. One of those is the digital agents problem, and we'll talk about how we're getting to that. But so some opportunities in the space today from the research perspective is basically building models that can just do a way bigger set of tasks, more similar to what you saw with Gato, right? Not just specific robotics tasks, assessing them across all of these different tasks, and making sure that they do reliably well, not just in physical action scenarios, but in digital action scenarios and action scenarios that kind of map to knowledge work, which often are very language heavy or very sort of image heavy, but maybe not video heavy. And then how do we sort of have a standard for how well models of this new class that are emerging will do? These are sort of a set of opportunities that we've been exploring. And I think that's a perfect segue for Pranav to start talking about multinet, which is what we've been working on for a couple months.
Yeah, sure. So multinet's been our biggest project that we've been kind of heads down on for the past like 2 to 3 months. So this slide is just basically giving an overview of like why we started multinet, what our thesis is, and what the major goal of this project is. So I think as Harsh mentioned in the past few slides, this whole emerging category of VLAs, even like the generalist models that exist going back to Gato 2022, was really our inspiration for like building an entirely new class of foundation models that are much more generalist and are much more capabilities focused than just the content generation model that exists today. And so our thesis for like this project, and also like one thing we should clear up is that our notion of vision language action is slightly different from like the VLAs that's mentioned in Octo or OpenVLA. So for them, the way like they talk about it is that it's vision language grounded action. So it's still only focused on like completing, like embodied actions or RL based tasks. We want vision language action models to be really good at vision tasks, really good at language tasks, really good at vision language tasks and also vision language action tasks. So we want them to be completely generalist, work across a variety of modalities and tasks. So our thesis is that, if you can like pre-train a model on like web scale multimodal data and tons of reward-based action trajectories, which is basically what RL or robotics data is, this will like result in an entirely new class of like foundation models that can do long horizon planning, interact with the environment, and actually reliably complete actions in an agentic manner. And so like this project can be like broken down into three major goals. The first thing we wanted to do is consolidate and open source the largest vision language control data set. And second, as Harsh spoke about earlier, we did want to build a benchmark for this data set and evaluate all the state-of-the-art foundation models on their generalist capabilities.
Can you open your Slack and pull this up? It wasn't even good.
Sure.
Yeah, give us 1 second. We want to show you a really cool, like, sort of demo visual of like what this data looks like, so that the rest of this talk actually makes sense and hopefully is interesting.
Which one?
There you go. Hopefully this works. Zoom, are you still able to see the screen?
No, I stopped.
Oh, okay. Give us 1 sec. We're sharing again. Oh, you just want to go to the page I was on for you. Go back. Keep going back. Keep going back. Oh, right.
This one, yeah.
There. Let's just scroll down here. Are you sharing?
Yep. I'll share now.
Okay, perfect.
Wait, can't see.
It's one of the arcs, probably, right?
Yeah, I don't know why it isn't showing up.
Scroll down. There it is. Cool. Okay, so Zoom, you should be able to see. Can you verbally confirm for us?
Yeah, looks good.
Awesome. Excellent. Thank you for your patience. So basically, this is just an overview of, like, these are very specific samples of the data that's in this data set. This data set is orders of magnitude more than the samples you see. Obviously, it's like thousands times more. It's trillions of tokens, or like close to 100 TB in data. But just to give you an idea, so if you scroll up a little bit, Pranav, so this data set covers, of course, standard language and vision, but also tons of 2D simulations, which correspond to games like Atari and things like that. As well as like what you think about with locomotion simulations. So this is starting to map more to like how you might think of the action models. And then also dozens of tasks in manipulation, proprioception, many of which are recorded from real world robotics trajectories. So this is like a good visual of the kind of data and the kind of tasks, that's a good spot, kind of tasks that these, this benchmark is assessing, that we expect these models to be able to do well. And really the models that we are also building will be able to do well on. So cool. Now we'll clunkily shift back to the presentation, to bear with us. Yep, you guys are able to see the Google Slides now, right?
Give it a second. It's saying it's started screen sharing.
I think you need to hit resume share. Yeah, hit it.
Yeah, I'm hitting it. I don't know.
Share again. There you go. Is it sharing now?
Yep, looks good.
Perfect. Awesome. Thank you. Cool.
1 second. Yep. Cool. Yeah. So, why is this? Okay, whatever. Cool. Yeah. So, yeah, like Harsh mentioned, so our data set basically comprises of a wide variety of modalities, tasks. And why do we need, this benchmark? So there are a lot of benchmarks that exist today that evaluate a bunch of different things for these foundation models, but they're super specific to like a given modality or like a set of modalities or like a specific task. So it probably evaluates, how good the model does in language tasks, how good it does vision tasks or vision language tasks, or completely separately how it does, how well it does in control tasks. And even within the control kind of space, there isn't a standard benchmark. With all these new SOTA models coming in, like OpenVLA, Octo, they all evaluate with different metrics, and there's not a lot of standardization around these benchmarks. So we think that, like, given our data set and given our thesis, the direction in which we want like this new class of foundation models to go in, it would be appropriate to have a challenging benchmark that kind of evaluates this generalist capability that we're talking about of all these models. And we really think that if we can showcase, the gap in the space currently, it will pave a way for like a new class of foundation models that are not solely limited to content generation. So you can like kind of think of it as three major research questions. So how well do the current state-of-the-art VLMs like the GPT-4o, adapt to action trajectory tasks, which are basically your robotic offline RL data in the form of robotics like OpenX? And then how well do the VLAs like Octo, OpenVLA, how did they adapt to just image understanding, language understanding, and vision language tasks, and not action-based tasks? And there are also some generalist models that exist today. For example, Hugging Face's Jack of all trades model is basically their attempt to replicate Gato in an open source manner. And how well do they perform, and what are the real challenges for these models, and how it can be improved? So that's like basically our idea around this benchmark, why we want to do it, and yeah, why we're working on it. Yep. Yeah. So like I'll start. So the multi-net project is kind of divided into like the data set, the benchmark, and the profiling of the state-of-the-art models. I'll dive deep into the data set aspect now. So the past couple of months, we've basically been heads down, majorly working on the data set and benchmark aspect, and we've consolidated our entire like V0 of like multinet. It's several trillions of tokens worth of open source vision language, RL, robotics data across a wide range of categories, like a ton of vision language tasks, and then even for control, navigation-based control, locomotion-based control, manipulation, and like game-based like Atari. And we've also fully open sourced the code base for this. So anyone can easily like download one or many or all of the data sets in V0, and also translate all the control data sets from a variety of sources and formats to one unified format so that it can be used easily. I'll kind of like go into this a bit deeper in the following slides. Yep. So kind of where we started off with this data set is, Gato's list of data sets.
We should clarify, by the way, I realized this wasn't communicated earlier. Gato never released, like DeepMind never released any model. They never released any data sets for a lot of these are, a few of these are sort of common data sets, but many of them you'll see like DM Control Suite, they're proprietary data sets. And so this is a big blocker, right, in the field. Like there hasn't been good data to substitute for these. And so it was quite a task to basically figure out what the good alternatives are, hunt them down, consolidate them, and then map them over.
Yeah, I'll like kind of dive deeper into like what we did, what are the challenges we faced, and stuff like that. So basically, this is where we started off. And like Harsh said, many of these data sets are internal to DeepMind. And we actually had the opportunity to like collaborate and speak with and get feedback with like a senior research scientist at DeepMind. And some of the data sets like Atari Extended includes like, 10 extra environments that almost no one has access to. I think he mentioned that they had a specific partnership with an organization that gave them the data. So there's almost no way you get this data. And Playrooms is actually a funny one because it's literally only mentioned once in the entire paper with no citation. So like there's no way to find that data. And then there's also these other environments like Sokoban, Modular RL, which are super old repos. So it's very hard to like, reproduce, get it to work. and they're only environments. So we need to train our own reinforcement learning agents on it and then generate expert episodes. And we didn't think it would be appropriate to spend way too much time on this for like a V0. So we wanted to get something out that had all the capabilities that we wanted it to have, but also people could start using it as soon as possible. And it's also been like 2 years since Gato came out, and it's been an incredible like time for the space. So there's been some amazing, super high quality open source dataset releases for like all of the fields like vision language, RL, robotics. Yeah. So diving deep into like the vision language aspect, even when we started like finding open source alternatives to what Gato had, we faced a few challenges initially. For example, like Pile, which Aluther AI came out with, was one of the largest like text corpus data that was open source. But it turns out that it isn't like hosted through like, DI, which is where it was initially being provided. It was initially being provided. And I think the ML and AI community, they just like share with each other out of goodwill, and you can only torrent the data. And for Leon, they redacted it because of ethical issues. So we had to like go out and find some really high quality alternatives to these that are at that scale or bigger and open source. So Obelix is a great interleaved image text, per data set. On the bottom right, you can kind of see they have a really cool like visualization, which basically categorizes their data, and you can click on it and see what kind of data there is for these image text pairs. And then there's also, Koyo 700M, Datacomp 1B. These are all image text pair data sets. And then a really cool language data set that we found was the FineWeb Edu. So Hugging Face released the FineWeb data set itself, but a much more filtered version and curated version of that is the FineWeb Edu, which is basically text only from educational web pages. And this kind of blew up after like, I think Andrei Karpathy tweeted about it, about how like, he basically tweeted the chart that's at the bottom of this slide about how LLMs can learn much faster and better if the content is educational. So, we really like kind of look for a high quality open source alternative, and this worked out. Yeah, and there are many more data sets in our vision language list, which you can find on our GitHub.
We'll share, all links will be shared.
All links will be shared. Everything's on our GitHub, so you can find that. So for RL and robotics, we have like Harsh said, we have OpenX, but we have much more than OpenX as well. There's RL Unplugged, which was actually open sourced a few years ago by DeepMind, and it was basically their benchmark for offline RL tasks, and through that work, they open sourced a lot of their data sets. And then there's ProcGen, which are like basically procedurally generated game-like environments by OpenAI. And then obviously with Hugging Face's JAT, they train agents on, like 4 gym-based environments, Baby AI, Majoko, Atari, and they generated expert episodes and open sourced the expert episodes. So we have, data from that as well. And these are just some of the most important ones. We have many more in our list, which again, you can find on GitHub. Yeah, so a lot of our time went into kind of like consolidating this RL and robotics data and standardizing it to a common format. A lot of challenges we faced were, a lot of these data sets, especially in the RL space, are super ancient, very badly maintained, all from different sources, a variety of like formats, schemas, and almost like impossible to like reproduce. And one major like research decision we had to make along the way was identifying a common dataset format to convert all these control datasets to. So we were debating between like TensorFlow datasets, PyTorch, and Minari, which is like a dataset format by the Farama Foundation, who do a lot of open source RL work, especially recently. And the reason we kind of, so we ended up going up with TensorFlow datasets. The reason being, obviously, the TensorFlow community is incredible. It's super large, a lot of support, very mature, a lot of helpful libraries that help you convert datasets between formats. And of course, TFDS is compatible with PyTorch data loaders. And usually any data that's in TensorFlow datasets, especially if it's offline reinforcement learning, follows the specific schema called RLDS. And so that the way that schema is basically, episode after episode, and within each episode, it's like step after step. So it's pretty straightforward, sequential, very easy to understand and use. And a lot of the newer, like, state-of-the-art open source robotics and RL data have also been released in TFDS. For example, OpenX is completely in the TensorFlow datasets format, and in the RLDS schema, and language table as well, and other open source release by DeepMind. So we decided to go with TFDS, and it has proven to be a good choice because we have a script that allows you to translate everything to TFDS, and it's great.
I think the major takeaway on this front, like, we're enumerating all these challenges that we ran into. These are like pretty significant challenges in getting this data to be usable at all. And these are like data sets that should be usable. This field is super nascent. And we're running into it because we're trying to consolidate and like build this massive new thing that we expect new models to be trained on. But you can see how sort of like, fragile is not the right word, but how nascent everything still is. And formats aren't preferred. There's no good standards. Infrastructure hasn't really stabilized. So if we really want to push forward, and if, sort of like the agent community or the field of machine learning wants to push forward on building really complex systems, some of these problems will have to be solved. We're like duct taping this thing together just to make it work, but these are pretty significant challenges. So there's not a lot of interoperability, a lot of shared understanding across any of these. It took us like weeks to hunt some of these things down. Authors who built these libraries, they don't remember anything about them. And they're supposedly running, like, underlying some of the most sophisticated AI technology out there. So, yeah.
Yeah, it was pretty cool to reach out to some of these authors, and they were like, they just forwarding you to the next author. Nobody knows it. But yeah, so a lot of our work went into that. And so, like, looking more closely at the OpenX embodiment, because that is really one of the hottest, like, offline RL data sets today. A lot of the state-of-the-art models are being trained on it, evaled on it. And it's just a great, like, data source because it's from, like, a wide variety of universities, a bunch of different robot embodiments, and a bunch of different tasks. So, it's really high signal. And so I just added this like snippet of how like one time step of like a shard of one data set in OpenX looks like. So, it has like your actions, your rewards, your observations, and within observations, you have like, image-based observations, and then the observation state itself. And then you also have like your language instructions, language embeddings. So a lot of great information in it. It's also in the TFDS format, RLDS schema, so super easy to use. And like I said, wide variety of tasks, a bunch of different embodiments, like, and so, this is one of like the most important releases in the space of late. Yeah, and one thing you'll notice when you look at works like OpenVLA and Octo is that they don't obviously use the entire OpenX dataset because it's massive, and these models aren't even as big to kind of like capture all the information in these in these datasets.
And just to clarify, sorry, when we say they're not using like, a large amount of this data set, we're not just saying it's like they're using small percentages across all these tests. Often, like the models I was talking about earlier are like handling small subsets of these tasks. So they're not tackling everything that OpenX covers. These are like separate, independent things that a model, like theoretically, as AI should be able to do. And these VLAs are not yet tackling all of those tasks. So this is really like table stakes for if you want to get into the larger scale of action. It's like it should start to perform reasonably well across a lot more of OpenX. And that is not something yet that's happening either. Just to give you an idea of how early things are.
Yep. And so like we also wanted to kind of like curate this data set to get, like a very high quality subset of this. But at the same time, we did want to err on like the larger side because, the data set itself is a big contribution and people can use it however they want or train or eval on it. So we did like a basic curation method where so the OpenX also like they provide a super comprehensive like spreadsheet about, each of the data sets within OpenX, all the different like aspects of the data set, for example, like how the action space looks, what kind of gripper was used, how many RGB cameras, and a bunch of other information like that. So we decided to like reduce like the first level of redundancy or remove it. And so we grouped the data sets by the robot that was used to collect the data set. And then within each of these groups, we compare the data sets on a few fields that we think is super important. So the robot morphology, the gripper type, the action space, the number of cameras, do they have language annotations? Does it have camera calibration? And does it have proprioception? And then a lot of the times you'll see that like two data sets within this group have the same values for all these features. So it's clearly redundant and you want to get rid of it. And yeah, like I mentioned earlier, we have OpenX and we have much more in our V0. And this is where a lot of our time went into getting this like navigation-based control data sets, locomotion-based control ones, game-based control ones, and manipulation-based control ones. And you can find like the list of these data sets and how we've categorized them, what these data sets are. We have links for all of these. They're all on our GitHub. You can like take a look at it if you're interested. And yeah, so like that's what we've been doing with with our data set, and code base wise, like we've fully open sourced the code that can download all of this and kind of like translate these control data sets into the TFDS format. But really what's super exciting is what we're working on currently. We've kind of moved past the data set and benchmark phase, and we are starting to profile state-of-the-art models. So we're working on like prompt engineering frameworks that help adapt state-of-the-art like vision language models like GPT-4o to offline RL trajectories so that they can like actually generate action data. And this can be done zero shot, few shot. We're also modifying the only current open source replication of Gato, which is a JAT, to kind of like generate actions not only for the four like gym-based environments that it was trained on, but all the control data sets that's present in V0. So we can showcase how there's much more work that's need to be done in the space. And yeah, so that's it for like our data set and code base. The way we went about our benchmark is we have these categories for our data sets, and then we kind of went about like mapping categories to the kind of tasks we want to evaluate these models on. So say like, if it's like a vision language category, what kind of tasks do you want to evaluate it on? And what are the data sets that correspond to these tasks? And what are the metrics that can be used to actually evaluate their performance? Of course, there's like a link to this where you can see like our detailed thought process and how we went about it. And our latest benchmark design proposal basically contains, the final list of like eval data sets and the metrics we're using for that. And we basically curated this, we designed this benchmark, and we went out and spoke to a bunch of authors and experts in this field who've designed benchmarks, have worked on it, and we're also collaborating with some of them now, professors from like MIT, UT Austin, industry researchers in DeepMind and NVIDIA. So they've been giving some great feedback. We've been iterating on that, and you can see all this in
Do you
links.
want to let's actually show them? Can we open
Yep.
that link? And so we want to just show you guys a. Yeah, I should just open. Yeah, I think it's still sharing. You're all able to see. We opened a Google Doc.
Yep, it's
Perfect.
loading.
Excellent. Okay, cool. So, yeah, do you want to just walk them through, like, just very high level? Like,
Yeah, sure. So like this is like the category-based mapping that I was talking about. So within like vision language, if you have a category of image captioning, what are the data sets that you want to evaluate it on? Visual question answering, what do you want to evaluate it on? There's like 4 data sets within that. All of these are super popular ones. And then image understanding, and then common sense reasoning for text, and then just purely text understanding like MMLU, which you've seen everywhere. And then like what kind of metrics do you actually use to evaluate these tasks and the performance of these models and these data sets? So we identified like metrics like cited for captioning, VQA accuracies, recall, log likelihood and accuracy. So this is kind of like our final like benchmark design. And I'll actually jump back to the slides and I'll talk about how we're thinking about the metric for RL and robotics. Yeah. So we've actually been thinking about like this research question, like what evaluation metric can you use for to evaluate the performance of models in offline RL trajectories? Because with offline RL trajectories, you only have observation, action, reward trajectories from like agents that have generated it, that have like interacted in the environment. You don't have access to the actual environment or like the policies themselves. So how do you evaluate it? So OpenVLA, Octo, they evaluate it using a metric called success rate, which basically tells you how many episodes has the agent or has the model successfully completed out of the total number of episodes. But that begs another question. Most of these models are only predicting the next action and not the next observation state. So if you're only predicting the action, how do you know if you've actually reached like the end observation state and achieved the goal that you wanted to? So we're thinking, like, do we need to like generate next observation states along with next actions? Or how do we think about this? And then another, metric we've been thinking about is a similarity metric between the model predicted trajectories and expert trajectories. So for example, if the model predicts like, 6 like tuples of observations and actions, how close is it to a trajectory that's been generated by the expert? So coming up with a metric to kind of like evaluate that difference between both of them. So that's kind of something we've been thinking about, and that'll be part of our like benchmark as well, so that we can evaluate the performance of models on offline RL trajectories. Yeah, and so like our next big sprint, which we're working on currently, is profiling the current state of the art models on this benchmark and all these data sets that we listed. Obviously, JAT is our baseline because it is probably the only open source like generalist model in the sense that we're talking about. And we also do want to like eval like the other state of the art models, like vision language models like GPT-4o or OpenVLA for VLAs, and we're going to be doing like zero shot and few shot evaluations using the prompt engineering framework that we spoke about. So basically a prompt engineering framework to evaluate GPT-4o on like these offline RL trajectories. How can you get it to generate actions? And then adapting the JAT code base, that will be zero shot, and then adapting OpenVLA to vision language tasks. And eventually we want to get to like fine-tuned evaluation where we fine-tune these, we modify these like models so that they can be fine-tuned on the data sets that are present in V0 and then evaluate them further.
But to be clear, the whole point of all of this is to actually, we'll see what happens. We're very sure this is going to happen. Show that these models don't do well, right? Like that they do really, really poorly, and thus motivate obviously what we are building. And we'll give a bit of a kind of overview of that, but also push the field forward. Like, dude, there's so much potential in action models. In creating this more standard, clear benchmark, can we at least build models that fulfill this? And we already kind of can see with the profiling that we're doing that like these models are not able to do this collection of tasks the way that they're oriented. So really excited to share that literally on the order of the next few weeks. Cool. Yeah. So I guess this is me now. Okay. Yeah. So I'm just going to talk a bit about, we've talked about action models, what they mean, what they are. We've talked about what they should be, how we're kind of trying to manhandle the world into training them that way and build these new kinds of action models. And now we're going to, I think like I wanted to give you guys a taste about how we think these, what we think the utility behind these are and how we think they're going to map to new kinds of systems and eventually even really useful multi-hop capable digital agents. And so we are actively training models to fulfill this benchmark as well. We are training models from scratch. Eric is sitting here in the front. He's a researcher at Manifold, and he's literally working on training these models from scratch. And we are also working on, like Pranav was saying, fine-tuning the current SOTA models and seeing if like can we get them to behave well and do some of this stuff as well. We're really trying to build really general action reasoners, and we're training them on this foundational skill corpus. But we don't just think of it as like an end-to-end model problem. We think there's going to be tons of software, tons of infrastructure. I'll give you like little sort of previews into those, but tons of infrastructure that will be really necessary to help these general, powerful action reasoners map to useful agents, whether that's embodied, which there's a lot of brilliant teams working on that front, as you've obviously seen, or digital agents as well. Let me go on forward. One thing I wanted to call attention to is like there's two ways to think about digital action. So some of you may recognize, literally, I think the last talk in this series was from Tianbao, who was the lead author on the OS Worlds paper. And in that, they provide a benchmark for these graphic user interface based action trajectories, right? And that is one way people think about digital actions. A lot of teams think about how can you have a model interact with, or an AI system, however you want to think about it, interact with software in the same way that a human does. So primarily enacting control through clicks and typing and things like that. And there's a huge obvious long tail of usage that maps to that. But in terms of actual maturity of technology, we're so early. So OS Worlds is an amazing contribution and is the sort of furthest ahead by far. But they contain 360 tasks, and some of them are quite mundane, like open this file or move this, from this folder to this folder. And teams that are working on like the OS level manipulation stuff, they're pioneering the way on this, and it's still super early. So we see the models that we're building. It actually is almost like intuitive, right? That these models that are able to navigate these like 3D scenarios, these 2D scenarios that are different than necessarily your desktop, will also be able to transfer well. And so this is one class of actions that we hope to fine tune and show these new models that we're building to be effective on. Can we go on forward? The other thing that we've been thinking a lot about, which a lot of other teams and groups seem to not be thinking too much about, is trajectories of API calls. And so this is the reason, sort of in the beginning, you might recall I had mentioned function calling as primarily a language-driven task. But if you think about how intelligent analogs, like maybe humans, think about and interact with pieces of software, interact with APIs, interact with black boxes, we have some sort of model or representation of what should go in, what we're expecting out, that may be inherently multimodal, and we model that over many, many steps. That is a workflow, right, for us. And so this is perhaps a less explored area that we think is going to occupy a huge chunk of usage and will be really useful for AI agents in general. And our models, we're trying to basically transfer and fine tune them on this objective as well. And so we're working on benchmarks for this. We're working on how to fine tune these models. So we're working both at this foundational layer that we've basically spent all the day-to-day describing, but also this application area. And we're really excited about what we're going to have to show in a couple of weeks and months. The other thing is like, there's a huge amount of opportunity, and actually not just opportunity, necessity in defining various infrastructure pieces to make this happen. So we just barely touched on the interoperability issues, the lack of standards that are bottlenecking teams from just putting these various open source data sets together into a compelling consolidated benchmark. But in terms of evaluating these action models, what's shocking, and every time we describe these models to people, Pranav kind of talked about it earlier, these are not being trained and sort of being used in any real scenarios. They're just being compared to recorded trajectories. So these models are basically just memorizing tons of sequences and trying to learn from those sequences, but there's no real sort of interpretable environments that these are being used in. Because it's expensive. It's expensive to have simulations that work for these robotics models and things. It's also expensive to have that work for digital agents. So like you can take the OS Worlds idea and think about making it generative. How do you have open-ended scenarios, lots and lots of synthetic data generated to allow digital agents to use API trajectories or your GUI in the way that a human would? So there's enormous opportunities in building these fundamental tools. And one of the exciting things that you can see that are kind of an analog is projects like WebSim, which I think is also a South Park Commons company. They've done really cool work in basically building these alternative sort of like internet generators using Claude to basically generate dynamic, random, crazy, wacky versions of like websites and things like that. That same principle, sort of open-ended generation, could be really useful in enabling AI agents to do things successfully. And it's probably a necessity when you think about the order of magnitude that needs to be, of data that needs to be sort of generated to successfully make these models work in the long term. I think that's our last major slide. I just wanted to call out, you guys have stuck with us for 50 minutes of a very dry talk. I really appreciate it. I think we have a few minutes for questions, but I'll just touch briefly that there's a lot of ways if you want to help or you want to get involved. So we work with Manifold Research, which is an open source research group. Eric is here. I think there's a couple of folks in the Zoom that are probably also from Manifold. Pranav is also part of Manifold. I'm also part of Manifold. And we effectively, Medark was really a spin out of that group to work on scaling these technologies. So if you want to contribute to the open source side of this, please reach out. There's a well sort of formed collaboration pipelines and things like that. So would love to hear from you. If you want to work on building like what might be, one of the most impactful technologies humanity's ever seen, and you want to do it full time, just reach out to me and we'll figure it out, right? I'd love to chat. And I didn't mention this here, but if you're working on AI agents and you're running into problems around reliability, or just you have complex workflows that they might be greenfield and you want your agents to be able to do those, please chat with us. This is a long sort of almost like, this is definitely a frontier model effort and it's a long shot, but we want to work with as many agent builders, whether it's open source projects, companies, whatever, to understand how you expect the models to react, interact, and how you expect to use them so that we can better design these models to fulfill those use cases as well. That actually is probably one of the most important metrics to achieving very powerful AI systems. So yeah, our contact information is there. Please, we'll be here after to chat with us. Yeah, would love to talk. So. Keep the slides up. Danny, I think I know we're almost out of time, but if anybody has questions, we're happy to field them.
Sure. Yeah, we can start the Q&A session. If you have any question, please let us know.
Oh, what is the latest on the aggregate evaluation metric? Like if you got a bunch of different categories of tasks.
You mean for multi-net?
Yeah.
Yeah, you want to take that?
Yeah, so are you talking about like composability between the tasks, like vision, language, and robotics?
Like a unified.
Yeah.
So we were like thinking about that initially, like a unified metric, like one score. And we did talk to like some of those experts about that as well. And we aren't entirely sure if like a unified score will actually make a lot of sense. And I mean, we haven't like explored like the mathematical rigor that should go behind it. But I think there's also a lot of like useful information by giving these category-wise scores for these models. You can kind of like pinpoint where these models are lacking and where they need to be improved. So yeah, that's kind of an open question really still. If a unified score has a lot of like advantages.
It's like a sexy thing. We want to have like hey, here's a number, like this is how cool your generalist model is, right? Like this is how awesome and powerful it is. But I think the numerical dynamics are really hard to make work. And so it's not something that's like the top of the priority stack.
Yeah.
Right now.
It's almost like you need a better tool. Instead of a table of numbers, you need like a visualization tool to see the landscape of all of these models.
Yeah, true. Yeah, definitely.
So to follow up on that, is the question kind of, is there going to be a unified single number that would represent both BQA performance as well as like predicting trajectories?
Pretty much.
Kind of like different tasks.
Yeah. And the idea, like, you run into like, we just haven't, this is a very large project, you can imagine, bandwidth sort of strap, but like, there definitely are challenges in like, you just like normalizing like the scores that you might get from some of these evaluation metrics for like the trajectory stuff, control stuff, and then figuring out how to compose that with like, perplexity or something else.
Even like within like the control data, like a score on like an Atari game, doesn't, even if you normalize it to a specific range, doesn't really mean the same as like a score on like an OpenX data set, just because there's like a significant difference in like how hard it is or like the environments. Yep.
Also, the data quantity and like the complexity of tasks is very different.
Yeah.
So if you're gonna figure something like that out, you have to like, there's probably a huge amount of research just to figure out that score, like would be really cool though. Yeah. Yes.
How do you weigh the importance of a static like data set that begins like the training of like your larger generalist model versus like these online emulator environments that are like constantly like your model's working with to like for like I'm spending a lot of time in Android obviously.
Yeah.
But obviously every app like update changes like the UI like flows for, and not even like generally like people are pushing new like design paradigms all the time. Like how do you like separate this like online like reinforcement learning aspect of a lot of these environments that are constantly changing from external sources that you can't map to in like the static data set that you start with?
That is, I mean, that's like a huge question, right? I think that this is take number one, just to get like bootstrap models that work right now. How well they work. So for example, contextualize it, like on OS Worlds, I think, like the best performance, maybe it was from Claude, maybe it was from GPT-4, I don't know. Tianbo was sharing last week, the OS Worlds benchmark, it's like 12%, like, which is horrendous. Humans get like 75% on that benchmark. Are our models gonna get like 20%? I don't know. The current ones we're profiling, are they gonna get 15%? I don't know yet. So we don't even know the answers for like the fixed set, the corpus that we've assembled, what those are. I do think that ultimately, the amount of data you can create and just the sheer utility of the variance of like these kind of interpreted environments that you're talking about is actually what you need to train on to solve, right? So that's what I was sort of alluding to in the generative framework at the end, is like, how do you even start getting to that? And what are the, like, how can you, like, from a couple latent factors kind of start to represent all this? Ultimately, the transfer between like real like Android interface, right? Versus like what you trained on, there will always be like, it's almost like, it's not sim to real like in robotics, right? But it's like sim to production sim or something, right? And
Totally.
but like you have to do well on that for this to mean anything. So I think like the closest we'll get to is really good generators. But the cool thing about OSs, which is what you're doing, right, is like OSs are generators, right? They are environments. You have an interpretable environment. I think the problem is for a lot of the other control things, and also the API trajectory tasks that I talked about. Where the heck how do you simulate that? How do you interpret that? There's nothing
Right.
for that.
Yeah. Well, let me know when you want some Android emulators.
100%. Yeah, absolutely. Yeah.
We have a lot of them, so.
Yeah, David.
I wonder if there's been like any research, like following up on the metrics question of having something unified. And I know like the metrics are usually, not that great at determining how models are actually doing. I'm curious if there's been like any research on testing the models on like games, not like beating another player in chess or whatever. I'm talking like speed running a game, like instead of like trying to beat this metric, you're actually like, you put in an environment that's dynamic and whatever, and then you make like decisions there. Wonder if there's been like.
Yeah, I mean, I'm not an expert in that area, but I don't know if we have like some RL folks in there, but I would imagine like it depends on the game, right? So if it's like an open-ended scenario, I think there's some research now coming out from like DeepMind and groups like that on open-endedness, which is definitely where this also has to go. But we're like, it's just very far, right? But in terms of like beating Dark Souls or Elden Ring or something, or like one of these games,
That's what I mean.
okay, some games have, they're not, right? I was gonna get into the trap there. But like, I imagine beating Halo 3 is significantly easier, right? Because of the amount of sort of variability in what a player can do anyway, versus something like Elden Ring, right? Which is a much more open world game, but it still has sort of a fixed set. And then there's open-ended scenarios completely. I would expect, this may sound, I don't know, I haven't kept up with this field, but like, I would expect that on games that have like even like Elden Ring and things like that are like open world but like have fixed sort of outcomes. I'm sure the RL agents are getting really, really good because there's just a ton of data you can train on, and like it's solvable, right? It's a closed-ended problem. So I don't know if any video game folks have any thoughts on that.
There is that company that's doing the Minecraft agents. It's like Altera or something.
Yeah, Altera, like the NPC, the Minecraft.
Yeah.
Yeah, that's open.
That's open. Yeah, exactly. Yeah.
Can I ask a question about multinet?
Please, yeah.
Yeah. So you currently have multinet version 0. What would it take, and like what would greenlight it and give you like past the threshold of becoming V1? What would like satisfy that?
So V0 is, we will release V0. So the versioning that when we say V0, V1, we're thinking about iterative, like, so one of the problems with benchmarks is like benchmarks get saturated, right? And in fact, like you can make a case that in 2024, a lot of the labs won by beating benchmarks, whereas people qualitatively say like GPT-4 Omni is worse than Turbo or whatever the other versions are. I always get these mixed up, but like, they've gotten worse qualitatively, and like it doesn't do things as well as it used to, or it's not as expressive. And it's like, well, they're doing better on, all the like language benchmarks and all this other stuff, right? And so like benchmarks have this challenge that people like Noam Brown talks about this, that they are, limited horizon, either gameable. And ultimately, I think, and this is a position that we take, and many people take, I think is like, you probably want to take an iterative approach to continuing to design benchmark. Benchmarks can be overhauled, they can be updated. So the way we think about V1 versus V0 is like V1 might comprise many more difficult tasks, right? As V0 gets saturated. So we're kind of like just setting the stage to be able to ship, you know, newer benchmarks that capture the same capabilities, but maybe in more complexity going forward.
Okay.
Cool. Danny, was there anything we missed in the chat? I guess like maybe one more question.
No, no questions in the chat. Yeah.
Okay, cool. Well, then I guess we're done here. We'll be here for a few minutes if you guys want to chat about anything, but thank you so much for coming, guys. This was awesome.